Welcome to the topic stress and strain. In its natural state, a body is in equilibrium under the internal forces of attraction of its molecules, which depends on the intermolecular distances. When an external force is applied on the body, additional internal forces are produced in it. This disturbs the previous equilibrium of the body, and a new state of equilibrium is established by attraction of the relative distances of these molecules. The body therefore undergoes a change of size or shape or both. When the external force is removed, the internal forces tend to bring the body to its original state. The property by virtue of which the body regains its original size and shape, and when the deforming forces are removed, is called elasticity. When deforming forces are removed, the body may or may not regain its original shape or size completely. Accordingly, if a body completely recovers its original size and shape on the removal of the external forces, it is said to be perfectly elastic. On the other hand, if the body completely retains its modified size and shape, it is said to be perfectly plastic. In actual practice, it is very difficult to find any body that is either perfectly elastic or perfectly plastic. The actual behavior of bodies lies between two extremes. Strain. When a body suffers a change in its size or shape under the action of external forces, it is said to be deformed, and the corresponding fractional change is called strain. For example, if the length of a wire changes under the action of some force, then change in length per unit length is called linear or longitudinal strain. That is, linear strain is equal to change in length delta L divided by original length L. Being a ratio, the strain has no units and dimensions. There are three types of strains: linear strain, volume strain, and shape or shear strain. Stress. When no external force acts on the body, it is said to be in the normal state. When a deforming force is applied on a body, it offers a resistance on account of its elasticity to any change in its size or shape, and an internal force of reaction is called into play, which tends to restore the body back to its original form. The internal force is equal in magnitude to the external force, but acts in opposite direction. The magnitude of this internal restoring force developed per unit area of the body is called stress. Its dimensions are m into L raised to minus 1 into T raised to minus 2, and units are n by m square. Depending on the deformation produced in the body, the stresses are known as longitudinal stress, volume, bulk stress, and the shear stress. If the external force acting on the body is inclined to the surface, its component perpendicular to the surface measured per unit area is known as the normal stress, and the component acting along the surface per unit area is called the tangential or shearing stress. If the external force acting on the body produces a decrease in dimension, stress is called compressional stress, while force expansive or tensile force a tensile or expansion stress. Hooke's law. The stress is proportional to the strain provided the strain is small, or stress is proportional to strain, or stress by strain is equal to a constant. This constant is known as the modulus of elasticity or the coefficient of elasticity, and depends upon the material of the body. It is, however, different for different types of strain in the same body. It is known as Young's modulus, bulk modulus, and modulus of rigidity, according as the strain produced in the body is linear, volume, and shearing strain respectively. The dimensions and units of the modulus of elasticity are the same as those of stress. Elastic limit. In case of solids, if the stress is gradually increased, the strain too increases with it in accordance with Hooke's law until a point is reached at which the linear relationship between the two just ceases, and beyond which the strain increases much more rapidly than is warranted by the law. This value of the stress for which Hooke's law just ceases to be obeyed is called the elastic limit of the material of the body for the type of stress in question. The body thus recovers its original state on removal of the deforming forces within this limit, but fails to do so when this limit is exceeded, acquiring a permanent residual strain or a permanent set as it is usually called. The elastic limit is sometimes defined in terms of maximum recoverable load or forces deforming the body. Elastic hysteresis. Let us consider a wire suspended vertically from a rigid support. When a load is applied at its lower end, its length increases. When load is increased step by step and a graph is plotted between load and extension, a curve shown in figure 1 is obtained. Up to point A, the curve is straight line, indicating that the increase in length of the wire is proportional to the load applied, stress and strain, and the wire recovers its original length when load is removed. Obviously, A gives the elastic limit of the material of the wire. The part AB of the curve shows the rapid extension than required by Hooke's law. The increase in length of wire is partly elastic and partly plastic, so that if the load is removed at B, the wire does not recover its original condition of zero strain along BAO, but takes the path BC to come to point C with residual strain or a permanent set OC in it. On further increasing the load, a stage is reached when the extension increases very rapidly for very slowly increasing load BD. That is, the material of the wire flows like viscous liquid. This happens at point B, which is called the yield point. When the load is further increased, a point F is reached when the stress takes a maximum possible value. This is called breaking stress. The wire begins to thin down so that its cross section does not remain uniform, which results in an automatic decrease in stress portion Fe of the curve, and the wire snaps or breaks at E, called the breaking point. When the bodies are deformed under external forces up to elastic limit, they return to their original state when the deforming forces are removed. Some bodies like quartz, phosphorus, bronze, silver, etc. returns to their original state immediately after the forces are removed. Other takes appreciable time to do so, or, so to speak, only creep back to it. Example, glass fiber takes hours to do so. This delay in returning to the original state on the removal of deforming forces is called elastic after effect. We have seen that the strain persists even when the stress is removed and thus lags behind the stress. As a result, if a material be subjected to a full cycle of increasing and decreasing load, the strain is found to be greater for the same value of the stress when it is being unloaded than when it is being loaded. This lagging behind of strains is called elastic hysteresis. Different types of coefficient of elasticity. Young's modulus. When equal and opposite forces act on a body along one direction only, the change in length per unit length along that direction only, the change in length per unit length along that direction is called the linear or longitudinal strain, and the force per unit area of cross section is the longitudinal stress. Within the elastic limits, the ratio of the longitudinal stress to longitudinal strain is called the Young's modulus of the material of the body. If a wire of length L and radius R is subjected to equal and opposite forces F, thereby increase in its length by delta L, then longitudinal stress is equal to F divided by A, which is equal to F divided by pi r square. Let it be equation number 1. Longitudinal strain is equal to delta L divided by L. Let it be equation number 2. And the Young's modulus Y for the material of the wire is Y is equal to F divided by A by delta L divided by L is equal to F into L divided by A into delta L, which is equal to F into L divided by pi r square into delta L. Let it be equation number 3. If A is equal to pi r square is equal to 1 and delta L is equal to L, then Y is equal to F. Thus, the Young's modulus of a material is defined numerically as the force which doubles the length of a wire of unit cross-sectional area. The units and dimensions of Y are the same as those of stress, that is Newton per meter square and m into L raised to minus 1 into T raised to minus 2. Bulk modulus. When a uniform pressure is applied over the surface of a body, the volume of the body changes. The change in volume per unit volume of the body is called the volume strain, and the pressure applied is called the normal stress. The ratio of normal stress to volume strain within elastic units is called bulk modulus of the material of the body. If a force F is applied uniformly and normally on the surface of area A, which causes a change delta V in initial volume V, then normal stress is equal to F divided by A. Let it be equation number 4. Volume strain is equal to delta V divided by V. Let it be equation number 5. So, bulk modulus K is equal to F by A divided by delta V by V, which is equal to F into V divided by A into delta V. Let it be equation number 6. For gases and liquids, the normal stress is caused by change in pressure. That is, normal stress is equal to change in pressure delta P. Bulk modulus K is equal to minus V into delta P divided by delta V. Let it be equation number 7. Negative sign indicates that the volume decreases if pressure increases and vice versa. Equation 7 can be written as K is equal to minus V into dP divided by dV. Let it be equation number 7a. Gases possess two types of volume elasticities. First one, isothermal elasticity. Et is equal to minus V into dP divided by dV at T, which is equal to pressure P. Second one, adiabatic elasticity. Es is equal to minus V into dP by dV at S, which is equal to gamma into P, where gamma is equal to Cp divided by Cv. The reciprocal of bulk modulus is called compressibility. That is, compressibility beta is equal to 1 divided by bulk modulus K. Modulus of rigidity eta. When a body is sheared, the ratio of the tangential stress to the shearing strain within elastic limits is called the modulus of rigidity. If the lower face of a parallelepiped is fixed and tangential force is applied at the upper face of area A in figure 2, the shape of the parallelepiped changes and the strain is shearing strain defined as the angular displacement in radians of any lateral section like OA along the direction of tangential force. Shearing strain theta is approximately equal to tan theta, which is equal to x divided by L. Let it be equation number 8. Tangential or shearing stress is equal to F divided by A. Let it be equation number 9. So, modulus of rigidity eta is equal to f by a divided by x by L, which is equal to f into L divided by x into a. Let it be equation number 10. Poisson's ratio sigma. When two equal and opposite forces are applied to a body along a certain direction, the body extends along that direction. At the same time, it also contracts along the perpendicular directions. The frictional change in the length in the direction along which the forces have been applied is called the longitudinal strain, while the frictional change in a perpendicular direction is called the lateral strain. The ratio of the lateral strain to the longitudinal strain is called the Poisson's ratio. It is a constant for the material of the body. In figure 3, a wire of length L and diameter d is subjected to equal and opposite forces f, f along its length. If the length increases to L plus delta L and diameter decreases to d minus delta d, then longitudinal strain is equal to delta L divided by L, lateral strain is equal to minus delta d divided by d. The Poisson's ratio of the material of the wire is sigma is equal to minus delta d by d divided by delta L by L, which is equal to minus delta d into L divided by d into delta L. Let it be equation number 11. Negative sign indicates that change in length and diameter are of opposite sign. That is, if one decreases, the other increases. Theorems on stress and strain. Theorem 1. A shear strain is equal to the sum of mutually perpendicular compressional and extensional strains. Proof. Let a tangential force F be applied to the upper face AB of a cube whose section ABCD is shown in figure 4. Cube's lower face is fixed. The cube is thus sheared to the shape A', through a small angle theta. Clearly, the diagonal DB is elongated to DB' and the perpendicular diagonal AC is compressed to A'(C). With center D and C, draw arcs BE and A'(G) and radii equal to DE and CG respectively. Since the angle of shear theta is small, the arcs BE and A'(G) are almost perpendiculars to DB' and CA respectively, and angle BB' E is equal to angle A'(G) is equal to 45 degree. Now in triangle BB' EB' is equal to BB' cos 45, which is equal to BB' divided by square root of 2. In triangle DBC, DB is equal to square root of BC square plus DC square, which is equal to BC into square root of 2, since BC is equal to DC. Hence, extensional strain is equal to DB' minus DB divided by DB, which is equal to DB' minus DE divided by DB, since DB is equal to DE, which is equal to EB' divided by DB, which is equal to BB' divided by root of 2 divided by BC divided by root 2, which is equal to 1 by 2 into BB' divided by BC is equal to 1 by 2 into tan theta, which is equal to 1 by 2 into theta, since theta is small. Similarly, compressional strain along AC is equal to AG divided by AC, which is equal to A' cos 45 divided by AD into square root of 2, since AC is equal to BD and AD is equal to DC. Thus, a shear theta is equivalent to an extensional strain theta by 2 plus a compressional strain theta by 2 at right angles to each other. The converse of the theorem, equal compression and extension strains at right angles to each other are equivalent to half of a shear, is also true. Theorem 2. A shearing stress is equivalent to an equal extensional stress plus an equal compressional stress at right angles to each other. Proof. Consider the section ABCD of a cube of side L whose lower face is fixed and to whose upper face a tangential force F is applied as in figure 5a. The shearing stress P is given by P is equal to force divided by area, which is equal to F divided by L square. Let it be equation number 12. If F were the only force acting in its upper face, the cube would move bodily in the direction of this force. But since the cube is fixed at the lower end and hence an equal and opposite force comes into play in the place of this face. These two forces constitute a couple which tends to rotate the cube in clockwise direction. The cube, however, does not rotate. Hence, the face DC which is fixed exerts an equal and opposite couple by exerting forces F on the faces AD and CB as shown in figure 5a. Thus, a tangential force F applied to face AB gives rise to equal tangential forces acting along all the faces in suitable directions shown in figure 5a. The forces acting along the faces AB and CB give rise to a resultant force F root 2 along DB, and forces acting along the faces AD and CD also gives rise to resultant force F root 2 along BD. Hence, an outward pull is exerted along the diagonal BD at the corners B and D, resulting in the extension. Similarly, at each of the corners A and C, a resultant force F root 2 acts inwards along the diagonal AC, resulting in its contraction. Thus, a tangential force F acting on one of the face of the cube is equivalent to a force of extension F root 2 acting outward along the diagonal BD and a force of compression F root 2 acting inwards along the diagonal AC, figure 5b. Now, if a plane is drawn perpendicular to the plane of paper through BD and AC, this plane will have an area L into L root 2, which is equal to L square root 2. So, compressional stress is equal to force divided by area, which is equal to F root 2 divided by L square root 2, which is equal to F divided by L square. Let it be equation number 13. And the tensile or extensional stress is equal to force divided by area, which is equal to F root 2 divided by L square root 2, which is equal to F divided by L square. Let it be equation number 14. Hence, a shearing stress is equivalent to an equal extensional stress and an equal compressional stress at right angles to each other. The converse of this theorem, equal extensional and equal compressional stresses mutually perpendicular are equivalent to a shear stress, is also true. Now, let me wind up this session. The property by virtue of which the body regains its original size and shape when the deforming forces are removed is called elasticity. Strain is equal to change in length delta L divided by original length L. Being a ratio, the strain has no units and dimensions. The three types of strains are linear strain, volume strain and shear strain. The magnitude of this internal restoring force developed per unit area of the body is called stress. Its dimensions are m into L raised to minus 1 T raised to minus 2 and units are Newton per meter square. The different types of stress are longitudinal, volume and shear stress. Different types of coefficients of elasticity include Young's modulus, bulk modulus and modulus of rigidity. A shear strain is equal to the sum of mutually perpendicular compressional and extensional strains. A shearing stress is equivalent to an extensional stress plus an equal compressional stress at right angles to each other. Now, try to solve the given questions. First one, state the two theorems on stress and strain. Second one, explain Poisson's ratio. Third one, what is meant by elastic hysteresis. Fourth one, what is meant by elasticity. Fifth one, what are the different types of coefficients of elasticity. I can suggest some books for your reference. First one, Classical Dynamics of Particles and Systems, 4th edition by S.T. Totten and J.B. Marion. Second one, Mechanics, Statistical Mechanics and Relativity by Professor Vivekanandan P. Kadavur. Third one, Engineering Mechanics, 5th edition by J.L. Marion and L.G. Kreitz. Hope that you have enjoyed this session. See you in the next session. Until then, goodbye.